We're going to be doing a video review of WeBWork Problem 4 in Homework 04, the section on autonomous differential equations. Here we are given a differential equation x prime is equal to x plus 3 times x plus 1 cubed times x minus 0 squared times x minus 1.5. And we are asked to list the constant equilibrium solutions and indicate whether each is stable, unstable, or semi-stable. So before we solve this problem, let's first review what autonomous differential equations are. I have a little review sheet written here. An autonomous differential equation is one written as a function of the dependent variable. So in this case, dx dt is equal to f of x, where x is the dependent variable. And as you'll see, our constant equilibrium solutions occur when our f of x is equal to 0. Let's go on to these three different cases. Notice here that since our derivatives do not depend on t, which is the characteristic of an autonomous differential equation, we're going to see the same derivative as we go across, left or right, as we vary our t. And these derivatives, our direction field, will determine our solutions. Here, when our derivative is equal to 0, as we see it goes across, the behavior of the functions above and below characterize whether it is stable, unstable, or semi-stable. So here, when the derivatives are above or positive below and negative above, we'll see that the solutions will kind of converge onto this value, and we call this a stable case. I've even written a little phase plot over here. It goes positive, it goes up below, it goes down above. The unstable equilibrium case is the opposite. When you have the values, the derivatives below the equilibrium are negative, it goes downwards, and when it's above, then it goes upwards. So our solutions are going to tend away from this equilibrium. So we call this an unstable equilibrium. And semi-stable is the case where above and below have the same sign derivative. So here I've given the negative case where it comes down in asymptotes at the equilibrium, and then below it, it goes down. So it's kind of a mix between these two. So we call that a semi-stable case, and it's also semi-stable if it's both positive above and below. So these are what autonomous differential equations are, and what constant equilibrium solutions are, and what stable and semi-stable and unstable mean. Now let's go on to our problem itself. First, we need to find the roots of our differential equation of our function of x. And here it is easy because we are given a monic polynomial with its linear terms factored out. So our x prime is going to be equal to 0 when any of these linear factors are equal to 0. So when x plus 3 is equal to 0, we get x equals negative 3. When x plus 1 is equal to 0, we get x equals negative 1. When x minus 0 is equal to 0, we get x equals 0. And when x minus 1.5 is equal to 0, we get x is equal to 1.5. So these four are our constant solutions. And now, let's characterize them. What I will be doing here is I'm going to draw a little phase plot, which means let's say that this is our x. Down here would be negative 3. Here would be negative 1. Here would be 0. And here would be 1.5. We want to see whether the functions increase or decrease between these values. So with enough practice, you can kind of do this in your head. You know that this is a monic polynomial, so you know above, this would be above. Kind of know that this would be above. And then, since that's an odd factor, signs are going to switch, so it's going to be below. Since that's an even factor, the signs are not going to switch, so that's going to be negative. That's an odd factor, it's going to be positive. That's another odd factor, so it's going to be negative. And you know the signs switch depending on whether the values are above or below that root value. So that was kind of confusing, but that's just going to be there to give us a little guess for what our solutions are going to be. So let's draw out, that our derivatives are going to be equal to 0 at each of these values. So we know that these are our equilibria. And let's verify our little guesses. So above, let's see, we want to put in a value that is greater than 1.5. So a very good example would be 2. So if we test for x equals 2, we plug it in to this differential equation function there, we will get 2 plus 3 is equal to, 2 plus 3 is equal to 5 times 2 plus 1 is equal to 3, so 3 cubed is equal to 9 times 3 is 27. 2 minus 0 is equal to 2. Squared, what will that be 4? And then 2 minus 1.5 will be 0.5. The actual number here doesn't matter, so what really matters is the sign. So we know that the sign of this, since these are all positive factors, is going to be positive. So good. We know that our x prime is going to be positive above. So this is good. We know that it's going to look something like this, since the derivatives are going to be positive. When x is in between 1.5 and 0, let's say for x is equal to 1, then let's check up there. We have 1 plus 3 is 4. 1 plus 1 is 2 times 2 to the third power is 8. 1 minus 0 is 1, squared is times 1. And now we have our negative 1.5. So if you look at this, it doesn't really matter what the number exactly is, we just know it's going to be negative. So our derivative is going to be negative, which means that this function is indeed decreasing. So this is going to decrease, it's going to look something like this. And so we've characterized our, first, if we look at our cases here, we see that it's coming down below and coming up above, and we know that it's diverging. So we know that satisfies our unstable condition. So 1.5 is going to be unstable. Now let's look at the case between 0 and negative 1. So let's say x is equal to negative 0.5. Then we plug it back up there. Then we get 2.5 times 0.5 cubed times negative 0.5 squared times negative 2. Now we see here that this squared is going to make this positive, and this negative 2 is going to make the entire thing negative. So this is indeed going to continue being negative. And as you saw before, this squared means that whatever's inside here doesn't matter, and so that's why I was able to guess that the signs are going to remain the same. So this is going to decrease, kind of like this. And as we see here, since we have both below and below, it comes down in, so it converges from above and it diverges from below. We have a semi-stable case, below. So our equilibrium x equal to 0 is semi-stable. Let's check below the case between negative 1 and negative 3. So let's check x is equal to negative 2. Negative 2, let's plug it back in. We have 1 times, we have negative 1 cubed, negative 2 squared, negative 3.5. So here we are going to have a negative, a positive, and a negative. And two negatives will make this positive. This was a negative. So here we will have a positive. Indeed, it's increasing, so it will look something like this. Our solution will look something like this. So as we can see, the solutions are converging upon this x equals negative 1 solution. So here, as we see here, in this case, when it comes down and it comes above, this is going to be a stable solution. And now let's check again for x is equal to, say, negative 4, which is below negative 3. Then we plug it back in up there, and we get negative 1 times negative 4 plus 1 is negative 3. Negative 4 minus 0, negative 2. Negative 4 to the power of 2, I mean. And negative 4 minus 1.5 is negative 5.5. So we see here, we have a negative, another negative, a positive, and another negative. So we have 3 negatives, and they'll give us a negative. So if our derivative is negative, then our function is going to be decreasing. It will look something like this. And you can see here that x equals -3, the values are diverging away from it. The values above are going to be, the derivatives are going to be positive. Below x equals -3, the derivatives are going to be negative. So we're diverging, matches this case right here, and we get an unstable equilibrium. So we are finally ready to state our solution. X equals -3 is unstable. X equals -1 is stable. X equals 0 is semi-stable. And x equals 1.5 is unstable. And that is the solution. These are constant equilibrium solutions, and these are their characters: unstable, stable, semi-stable, and unstable.